G'day and welcome to Luke's AC. I'm Luke, I'm a refrigeration lecturer here in South Australia and also a small business owner in air conditioning. On the channel we're going to be providing info on all things air conditioning, information for service techs on fault finding and inverters, as well as troubleshooting and service info for end users. If you like the content, don't forget to give us a like and subscribe so you can stay in touch with the latest videos. Cheers. G'day, this is Luke, and today we're going to be talking about inverter circuits. All our modern air conditioners these days are run with inverter compressors, and we're just going to give you an overview of some of the componentry that makes up the electronics to drive that compressor and give us the full control of our system. Now, some of these smaller splits might just have the one board in the outdoor unit, whereas some of the bigger ducted units could have 3, 4, multiple boards, and it's important to be able to know what the different components are and some expected voltages. That's going to help us fault find and troubleshoot the system, make sure that we're only replacing components that have failed, and give us some confidence in fault finding, making sure we got the right outcome for our customer and we can be confident in testing the system. So I'm just going to run through how the system works. Usually the first thing we come to is our filter components, power or filter board they might be called. So I'm going to draw it as though it's some separate boards, but remember, small system you may only have the one board. So we're going to start off, we'll have a filter PCB. We've got our incoming power into the outdoor unit. Here in Australia that's generally 230 volts AC, 230 or 240 depending on the state. But our incoming power is getting filtered. It has noise filters on the board, surge arresters and varistors that can protect the rest of the componentry from any spikes, but also noise filters, so the inverter itself can generate some electrical noise. We don't want that interfering with our product, our rest of our products in the home. So that's what the noise filters are for. So the filter board's really there to protect the rest of the equipment. It usually also has a current transformer on it that monitors the current draw of the whole system and gives a signal to our control board, letting it know what the current draw is. So that's our filter board there, and I'm going to draw underneath each of these what we've got going on with our sine wave. So to start with, we've got AC voltage, alternating current, normal AC sine wave, single phase. The next step is our diode bridge or bridge rectifier. Now, this is where we convert the AC to DC voltage. So I'm going to call it diode bridge or bridge rectifier. This point our diode bridge, we're going from 240 volt AC in to maybe 240 volt DC out. Sometimes we measure a little bit higher, but what we do have is a fluctuating DC voltage we end up with. So if we draw it on the sine wave, current flowing in only one direction, but it's fluctuating. So at this point, if we're measuring 230 volt AC, by the time we're coming out of here, we might be 230 volt DC. After the bridge rectifier, we will normally go through some power factor correction equipment. The Fujitsu products that I'm more familiar with, that includes active filter module, the reactor. So I'm going to draw those here on the board. And this is where we're starting to see the voltage get smoothed out somewhat. So I'm going to put ACTPM, which is active filter module, and my reactor coil, sometimes called a choke coil, coming out of here. We've got some of the fluctuations being taken out of the DC voltage. From there we usually go into a bank of capacitors, DC capacitors. So my capacitors here. Coming out of the capacitors, we've got a nice steady DC voltage. Typically, by the time we've gone through the power factor correction equipment, the capacitors, we're sitting around 320 volts DC, nice steady voltage. And once we've got that 320 volts, it's ready to be used for things like DC voltage back to the control board, but it's ready to be switched by the inverter board to drive our compressor. So the next stage is our inverter PCB. Inverter PCB. Some brands call this a IGBT, insulated gate bipolar transistors. Basically what we have here is our 320 volt DC coming in, so positive and negative. Sorry, I'll draw that. P and N. Typically when we're looking for this component on our boards, we're looking at P and N, and on the output side of the inverter, we have U, V, and W. The three phases going down to my compressor. Regardless of the brand, typically if we're looking for the inverter chip on our board, we're looking for P and N, U, V, W, and those three phases are going to be coming down here to drive my compressor. So I'll have them coming off. I might just be able to fit this in here. That's my compressor. And what I have got here this DC voltage coming into the board is being switched in such a fashion that when it's averaged out, it's giving me an artificial three-phase voltage. So not a true three-phase, but an artificial three-phase voltage that can be ramped up and down, and it can change the speed of my motor. So this is the inverter section. So we've converted from AC to DC, smooth the DC out, and then inverted it to drive the compressor. Now we can vary either the frequency, the hertz, or the voltage to ramp that compressor up and down, and that gives us control rather than the old systems where we'll direct online, compressor just banging in maybe with a soft start or a capacitor, running till it gets to temperature and turning off. With an inverter compressor we can ramp it up, ramp it down, try and maintain space temperature without having that inrush current every time the compressor stops and starts, so it takes a lot of the short cycling out of it. The compressor themselves, the inverter compressors, ultra low winding resistance. They're wired in star, so we can test if we've got it disconnected between U, V and W. very low resistance, down as low as 0.2 of an ohm, often between 0.5 and 0.2 of an ohm per phase. So that is a normal reading. We can also use our mega to make sure it's not down to earth, or our insulation resistance tester. So that's what we've got going on through the DC circuitry. There is always one other part of the controls for these units, and that's the main control board. So I'm going to draw that down here. So my main control board makes all the decisions. So it handles inputs and outputs. Like any other control system, we have inputs, giving information to my board, and outputs, things that the board is turning on and off. Now, inputs for a control board can be things like thermistors, signals from the indoor unit, from the wall controller. Perhaps there's external inputs have been connected to the unit. Anything that's telling the control board what's going on. So thermistors, transducers, pressure transducers are important. So thermistors, transducers. Current transformer from up on my filter board. The outputs would be things that we're turning on, so the inverter, the EEV, electronic expansion valve in these units gives us full control. The fans, DC fans. The main control board does the communication between the indoor and outdoor. Both indoor and outdoor will have a comms board or a main board that's dealing with that communication in both directions to the indoor. Now, this main board only works if it has got AC voltage coming into it and also DC voltage. So the AC voltage typically comes from the filter board, the incoming power, brings some 230 AC in, but it can't communicate unless it has DC voltage. So that comes from over here. It needs to also be getting that 320 volts DC in order to communicate. Some of these other communications are on different rails, so you might have 5 volt, 15 volt, but it needs to have the 320 volts DC here. So if I've got a comms error, a communication error on these sort of systems between indoor and outdoor, often people start with the main board. But if this main board doesn't have 320 volts DC, then it can't communicate. And that could mean I've got a problem up here through any of this DC circuitry that will hold out the DC voltage getting to my main board. So I could have a problem on my inverter, on my diode bridge, somewhere along there. We can go into how we test those components later, but this is just sort of an overview of the different equipment that we have in the inverter. So we've spoken about the compressor. It is possible to put an inverter checker on here in place of the compressor. So we unplug the compressor and put in an inverter checker, see if we're getting an output from the board. But typically there are ways of checking a lot of these components, making sure they're all okay. But if you've got your head around what sort of voltages you're expecting, you can go through and look for those. As I said, some of this model will be in one board. If you've got it all in one board and you've got no comms coming out of that unit, then you know that outdoor board's failed. You need to look at what's caused it to fail. has a DC fan taken out the board? Has the compressor shorted and taken out the board? Or has the board just failed? Maybe it's got a mouse or a gecko in it. Maybe it's had a power spike. But knowing how to test these components and what voltage we're expecting, hopefully this is going to help you fault find units in the future. So that's just the outdoor, but you'll find a lot of the indoor units, especially on the big ducted, where they're running DC fans, they're going to have a lot of this componentry as well. So you've got the AC going in the indoor unit. Again, there's going to be a diode bridge in there, changing the AC to DC. There's going to be capacitors. There's going to be some form of inverter, or like the DC fans here, they've got their own inverter board built into the back of the fan motor. So they're getting a signal from the control board to run, telling it how fast and giving a signal back that it is running, but it's got its own board in those fan motors speeding it up and down. So that's a bit of an overview. Hopefully that helps you in your fault finding down the track. Thank you.